Alright, so in Chapter 7, we're going to be looking at scatterplots, associations, and correlations. So, let's say that in this case we're looking at a graph that has, let's say that it's GPA. Or actually, let's say that we're looking at a graph of IQ versus GPA. Okay, and let's say that it looks something, it has a moderate correlation, association, looks something like that. So the higher one's IQ, the higher their GPA tends to be, but that's not necessarily always true. Like a guy like Einstein had a very high IQ, had a very low GPA. So just because you have a high IQ does not mean you'll do well in school. A lot of people with high IQs are bored in school and don't necessarily get all straight A's. And then you get somebody with a lower IQ that works harder and they do better in school. So what we're talking about is we have two variables here, and you have learned about this in algebra. You called IQ the independent variable and GPA the dependent variable. Well, we're going to term these a little bit differently. We're going to call this the explanatory variable in statistics. This is the one that is explaining what's happening to GPA, and GPA we're going to call the response variable. So the explanatory variable attempts to explain the response variable. So you would use the explanatory variable to predict the value of the response variable. So for instance, if somebody had an IQ of 100, what would we expect their GPA to be? Okay. In a scatter plot, the explanatory variable always goes on the horizontal axis. Yeah. So in this graph right here, in this situation right here, IQ is explaining GPA. Okay. So in problem 1, we're going to identify the explanatory and response variables and state whether they are categorical or quantitative. Researchers measure the heights of children at age 6 and again at age 16. So what is the explanatory variable? Well, it's age. They're using age to predict what? Height. Both age and height are quantitative variables. B, a political scientist selects a large sample of registered voters, both male and female, and asks each voter whether they voted Democrat or Republican candidate in the last congressional election. Okay, so what is the explanatory variable here? Well, in this case it's gender. And what's the response variable? Who they voted for. Well, we can't make a scatter plot out of that because these are categorical variables. We can only do a scatter plot with two quantitative variables. So we have no way of making a scatter plot in that section, in that second problem. So we would not be able to do that. Alright, so now let's look at associations and scatter plots. So a scatter plot is used to graph the relationship between two quantitative variables for the same individuals. Each individual represented on the graph by a point. So up here in our little GPA versus IQ, each one of those points represents a person. Okay. two variables have a linear association, sorry, both have a positive association, not linear, positive association when both are increase or decrease together. They have a negative association when they decrease together. So there's a positive. And this is a negative. I'm sorry, a negative is when one increases and the other one decreases. Okay? So, for instance, we would expect a positive association to be GPA and SAT score. We would expect people with higher GPAs to get higher SAT scores in general. That doesn't mean everybody that has the highest GPA will get the highest SAT score, but in general we would expect that to happen. Okay. Over here we might use the temperature and then sale of winter clothing. So as the temperature increases, we expect the sale of winter clothing to decrease. Those would have a negative relationship. As temperature, one's increasing, the other one's decreasing. And the other one is they have no association. So you get something like this. Something that looks like that. So let's say that we were to look at shoe size and GPA. Now, we would not expect shoe size to be a very good explanatory variable for GPA. Okay. Now, when we talk about describing scatter plots, we're going to talk about four things. We're going to talk about strength. And when we talk about strength, we're going to talk about strong, moderate, weak. Form. And we're basically going to talk about three things in this course, though there's more. Form could be linear. Form can be curved. Form can be parabolic. Or really the fourth option is form could be none, like this case right here. Direction. And direction is going to be positive or negative in general. Does it go up or down? And outliers. Okay, so strength. This is strong. Okay, this is moderate. This right here is pretty strong, though not linear. And it's a pretty strong relationship. Direction, this is positive. This is negative. And this is really, we don't know. So we don't know what the direction is. Form, linear, curved. Here's a curved relationship. And here's a parabolic relationship. Unusual features. We have an outlier. So that person right there. So let's say that if we were comparing IQ to GPA, that person has an unusually high GPA for their IQ. Okay. And then this right here, okay, that would also be considered an outlier. You can argue these two might be two, but this one definitely is. So strength, form, direction, and outliers. So let's see. In the examples below, describe what you would expect the form, direction, and strength for each to be. So drug usage and pain relief. Okay. Well, So if I am really in pain and I start taking drugs, what would probably happen is the pain would go down. Now, the more drugs that I take, it would probably level off to where it got to minimal pain no matter how many drugs I took. Well, you'd probably be passed out if you took too many drugs, and then the pain would go down to zero. But let's assume that we're kind of taking these not all at once, we're taking them over time. So what's the direction? Well, the direction is going to be negative. The form is going to be curved, and the strength of it is going to be, I would say, moderate. Why? Because different people respond to drugs differently. Not everybody's going to respond exactly the same way. Okay? Second one, calories consumed and weight loss. And weight loss. Alright, so as less calories are consumed, we would have more weight loss. And as more calories are consumed, we would have less weight loss. So we would probably have something like that. So the direction again is going to be negative. The form is going to be, I would say, linear. And the strength again is going to be moderate. Don't forget there's other variables that contribute to weight loss other than calories, such as exercise habit, hours of sleep, and score on a test. Well, you might argue that what if somebody pulls an all-nighter and gets a really good score, which could happen. Just because you get more hours of sleep doesn't mean you're necessarily going to do better on the test. So this is my guess is going to be fairly I don't know what the direction is going to be. I would say the form is going to be weak. The form is going to be I don't know, you could argue linear, and the strength is going to be weak. I guess we could say this would be positive. But just because you get more sleep does not necessarily mean you'll score well on a test. Though, you can argue if you really know this stuff, you know, you go to bed and you're not worried about it, so you sleep through the night. But then again, if it's a really, really hard test and somebody pulls an all-nighter and they score fairly well, so there's a lot of different scenarios depending on the type of test it is. Shoe size and GPA. I don't know what the direction that act's going to be. The form, probably, I don't know if there would be a form, and the strength would be weak. Age of car and cost of repairs. Well, you can argue, well, the car has a warranty, so the cost of repairs would be nothing for like 5 years. Okay, so when you first get a car, the cost is going to be very low. You know, you got to just change the oil and all that stuff, and then all of a sudden, you know, the warranty wears off. So what starts to happen is the car starts to go up. So this is going to be positive. This is going to be positive, curved slightly, and I would say moderate. Why? Because it depends on the kind of car you buy. Right? If you buy a Toyota or a Honda, your car repairs may not be that much money. But if you buy another brand of car that you know, all of a sudden around 75,000-80,000 miles, you got to start putting money into it. So it's also going to depend on the brand of car that you buy. Time for a mile run and age. Okay, this one's tricky. Mile time. Well, when you're first born, this could take forever. Then you're like 1 year old, and it would take you less time, and then 2, and then all of a sudden you get, you know, you get into your teens. You know, let's say you're I don't know, 9 or 10, and then you get into your teens and your 20s, and then what happens is you start to get old again. So guess what? It's when you're newborn, it would take you a long time. When you get real old, it would take you a long time, and in the middle, your time is going to go down when you're in your 20s and 30s, and then when you get in your 40s and 50s, your time's going to start going up again. So the direction in this case is, you know, it's both negative and positive depending on when we're looking at it. The form is parabolic, and the strength again is moderate. Depends on gender, depends on you know, your physical well-being, depends on your exercise habits. So there's a lot of variables there that contribute to this. Alright, so correlation. So correlation measures the strength and direction of a linear relationship between two quantitative variables. It is possible to have a strong association but a weak correlation. Now remember, this is about linear relationships. So I could have a strong relationship that would have a weak correlation. Okay, another example would be this. Strong association, weak correlation. Why? Because it's not linear. Another name for correlation is R value, or correlation coefficient. When there is a positive association between variables, the R value is positive. So for instance, this would have an R value that is positive. When there is a negative association, the R value is negative. So your R value in this case over here would be negative. Negative, not -1, negative. Okay. The R value is a value between -1 and 1. An R value of 1 indicates a positive, perfect positive linear relationship. So here's an R value of 1. Perfectly straight line. An R value of -1 indicates a perfect negative relationship. So that would look like that. Be careful. Neither one implies causation. So neither one of these two cases, where R equals 1 and R equals -1, means that this explanatory variable causes this response variable to happen. All we can say is that there's a very strong association between the two of them. An R value close to 0 generally means there's a weak linear association. So a correlation of 0 is generally something that is like this, where you would have a fairly horizontal line going through it. Remember, a correlation of 0 means it's neither positive nor negative, so it would be horizontal. However, the case you got to watch out for is the exception, right? Here's a strong association that has a correlation of 0. Perfectly straight horizontal line. So both of these have an R value. This has an R value of approximately 0. This has an R value of 0. Okay, so I'm going to go through how to calculate correlation, and it's this formula here that's on your AP formula sheet. So if I put these points in my calculator, so I have them in L1 and L2, and I go to stat plot, and I turn stat plot 1 on, and I put it on Scatterplot, and I go to zoom 9. There is my Scatterplot. So it looks like this. So I got to describe it. Well, I got to talk about strength. So this is strong. Form, linear. Direction, positive. Unusual features, none. So strong, linear, positive. relationship between x and y. Well, what are x and y? We don't know. Okay, but we do know that there's a strong linear positive relationship between the two of them. So now I'm going to go through the calculation. So I need to do the z-score, I need the mean. So I got to do one bar stats for the x values, which is list 1, these guys here. So this has a mean of 30 and a standard deviation of 15.8. And I'm going to do the same thing for list 2. And that has a mean of 90.2 and the standard deviation of 47.5. Now we need the z-scores for x. So to do a z-score, remember, z equals each value minus the mean, in this case x bar, over the standard deviation of x. Well, all I'm going to do is I am going to go to list 3. I'll clear these out and I'll show you how to do this. You could just follow along with this because I'm not actually going to ask you to do it, I'm just showing you how to do it. So I got to take each of these values. So I'm going to go to list 3 and I'm going to put parentheses. I'm going to say take each value in list 1, subtract the mean of 30, close parentheses, that's the top of the fraction, and then divide by the standard deviation with 15.8. That's going to give me those z-scores. So that's negative 1.266, negative 0.6329, 0. Well, that's right at the mean, so right at the mean has 3291 has a z-score of 0 and 1.2658. And then I got to do the same thing for the y values. So the y values are in list 2. So parentheses list 2. I'm now in list 4. So I say take list 2, subtract the mean of what's our mean? 90.2, and then divide by the standard deviation of 47.5. And that comes out to negative 1.267, negative 0.6779, 0.1010105, 0.58526, and 1.2589. So we got zx, zy. Now I got to multiply them. So I'm going to go over to list 5 and say, okay, take list 3 times list 4. Those are my z-scores, and I get 1.6043, which is simply this times this. Negative times negative is positive. And then this times this is 0.42905. This is 0, because 0 times that is 0. I get 0.37042, and then 1.5936. Okay, so we've done this part now. Now we got to add them up. So I'm going to let the calculator do that. So I go to, let's see, stat, actually it's second stat, and that gives me this, that's a list, and I want it to do math. So I want it to sum, oh, hold on, I need to go out to the home screen. Let's try this again. So go to second list, math, sum, and I need the sum of list 5, right? And it's 3.997335551, so 3.997. So that's what these add up to. Okay? And then I got to divide by n minus 1. Well, there's 1, 2, 3, 4, 5, so I'm going to divide that by 4. And I get a r value of 0.999. So in this case, r equals 0.999. Well, what does that mean? Remember, that describes two things. Strength. Well, where does the strength come? You compare it to negative 1 and 1. The closer it is to negative 1 and 1, the stronger it is. Well, 0.999 is really strong, really close to 1. Okay, well, let's look at our graph. We have a strong linear relationship. Okay, Now, just because the R value is close to 1 doesn't necessarily mean it's linear. You got to look at the graph first. And I'll show you some examples of that. And direction. Well, where does direction come from? It comes from the sign. This is positive, so our graph is positive. If this was negative, we would have a negative looking graph. Okay? So, we don't want to do that every time, right? So, if I go to second 0, which is second catalog, and I go down to diagnostics, this is something you should do. You see that diagnostic on? Go to that and do enter, enter, and when it says done, that means you've turned your diagnostics on. So now when I go to stat calc and I do a Lin regression, you could use either number 4 or number 8. I'm going to use number 8. All it does is it puts the y-intercept first, and I want it to do L1 and L2. Look what it gave us. It gave us the R value. Now you say, holy cow, Mr. O'Neill, it's like 0.998, right? Don't forget, we rounded here. This is a rounded number, this is a rounded number, this is a rounded number. These are all rounded numbers, so the calculator didn't round it, so the actual correlation is 0.998. Okay, so now we want to multiply by -2 and subtract 10 from each y value. Alright, so here's what we're going to do. We're going to go in, so the x values are not going to change. I'm going to clear out L3. So I just go up to L3 and I'm going to push clear, clear, clear. Alright, and in L3, I'm going to take list 2. So I'm going to say, okay, list 2, multiply it by -2, and then subtract 10. Let's try that again. List 2 times -2, and then subtract 10. Alright, so there we go. So you get -70, -126, -200, -246, and -310. Okay. And I want to go and take a look at that scatter plot of L1 versus L3. And let's see what that looks like. Zoom 9. Oh, look at that, it's negative, right? So we took this correlation and we made it negative. Now, if I go to stat and I go to calc and I go to Lin regression again, and this time I'm going to do L1 versus L3, and I calculate, and I just want to look at the correlation. My correlation comes out this time to -0.998. Now, the absolute value of the correlation, the strength of it, the strength of the model did not change. It's still very strong, but it became negative. Well, why did it become negative? It became negative because we multiplied by -2. So that changed the direction of it, but it did not change the strength of it. So what happens now is when we would calculate all these z-scores for these y values, they would all become the opposite sign. Okay, so then what would happen is when we multiplied this zx times zy, all those signs would change, and then our correlation would change signs. But the z-scores themselves would not change. So this would be positive 1.267, this would be positive 0.6729, 0.10105, so forth and so on. Okay, so the only thing that would change in this whole thing, this whole first equation, would be the signs. The zy's would change signs, and the zx times zy's would change signs. but the actual sum would now become negative 3.997. And then you divide by 4 and you get the negative 0.998. So remember, z-scores, the only thing that happened is the z-scores would change signs. Okay, that's why the correlation didn't change. Okay, so the strength of the model remained the same. Okay, so an R value is a standardized value. Why is it standardized? Because we use z-scores and therefore has no units. Converting the units of measurement of the data values has no effect. Alright. So let's say that we're looking at a graph of years of experience. And we look at dollars earned. And we have, let's say, I don't know, we're looking at CFOs of Fortune 500 companies. Okay. But we bring this graph overseas to Europe, and we want to convert dollars to euros. And let's say that the R value of the original graph was 0.8. Well, if we convert our euros, however, whatever the exchange rate is, our Y value would change. So we would, I don't know, multiply by 2.6 or whatever. I don't know, $1 is 2.6 euros, whatever it is. Okay. So what would happen? Well, the graph really wouldn't change. The only thing is the scale here would change, but the graph itself wouldn't change. We didn't multiply by a negative. So therefore the z-scores of the x values would not change. Okay, because they are standardized. Okay. So what would happen to the correlation? Nothing. So though we change from dollars to euros, the correlation would remain the same. Okay. So now what they want us to do, the next thing they want us to do is they say, okay, take the original plot. So I'm going to go to stat, edit. I'm going to just cancel out L3. And I'm going to say, okay. Now what they want us to do is to graph, switch the x and the y values. So I'm going to go to plot, and I'm going to make L2 my explanatory variable and L1, let's see, L1 my response variable. Okay. So then I go to zoom 9 and look what the graph looks like. Okay. So now what do? We go to stat calc and I go down to number 8 and I say, okay, make L2 my x variable and L1 my y variable and calculate that. Well, look what the correlation came out to be. Correlation is 0.998. So what would the description of this be? Well, this would be form. Let's see. I'm sorry, let's start with strength. Strong, form, linear, direction, positive, relationship between x and y. What's our correlation? Well, it's 0.998. Correlation of x with y is the same as the correlation of y with x. Why? Well, let's look at our formula. What do we do to these z-scores? The z-scores here wouldn't change. So what do? Well, we multiply them. Well, what happens when you multiply something in a different order? Nothing. So if I multiply 3 times 2, I get 6. So what if I multiply 2 times 3? Well, it's still 6. So the only difference is I'm just multiplying these in a different order. But these products over here would not change. So nothing in this whole calculation changes. So my correlation doesn't change even if I change the two values and make this y and this x, as opposed to up here this was x and this is y. Okay? So now we got to go and put these guys into our calculator. So let's see, we got 10, 20, 30, 40, 50, and we need 250, 205, 147.5, 103.2, 49.8. Okay, and then we're going to go zoom stat. Okay, so what happens? We get that guy right there. Description. We have strong, direction, negative, form, linear, association between X and Y. So what do we expect the correlation to be here? Well, we expect it to be a number that's going to be pretty close to -1. Let's see what happens. Stat calc, and again, you can use number 4 if you want. I'm going to use number 8. So statisticians tend to use that. And I'm going to do L1 versus L2. Now I'm going to say, okay, calculator, calculate that for me. Look at that, my correlation is -0.999. And that tells me two things. It tells me strength and direction. Well, this is close to -1, so it's strong, and it's negative, so that means that as X increases, Y decreases. Okay, let's look at the next one. We go to stat edit, we got 10, 20, 30, 40, 50, 60, 70. Okay, I'm going to clear list 2, and I'm going to put those values in 40, 80, 50, 90, 60, 80, 70. And then I'm just going to push, since I already have a stat plot on, the X list is L1 versus L2. I hope I did that last one right. I think I did. I'm going to do zoom stat. Okay. Just make sure that we did that right. Yep. Okay. So this thing looks like this, and we got that, and then this is here, and then that's there. You say, well, this looks like a function that goes like that. Well, that's not how functions go. That wouldn't be a function. Remember, a function is defined by the linear, by the vertical line test. So this is not. This is something that if I was to draw a line, I might draw a line that best fits something like that. Okay. And this is X and this is Y. So what's my, let's talk about strength. Now in this case I'm going to say this is moderate, and this is going to be positive. As X increases, Y is increasing. And I'm going to say this is a linear relationship because I could draw a line through it. It's not curved and it's not parabolic. And I don't see any real points that concern me, so I'm going to say that's between X and Y. And then what do I expect my correlation to be here? Well, I expect it to be positive. And I don't expect it to be near 1 here. It's probably going to be somewhere between, I don't know, 0.5 and 0.7. So let's see what happens. Let's calculate that. 0.43. Okay, so that's not real strong. Usually 0.5 0.5 or less is usually the line between moderate, so moderate, weak. Okay. Problems, there's not a lot of points here. Alright. Let's go to the next one. Go to stat edit. We got all the way up to 70, so let's put these in 100, 50, 200, 30, 0, 125, 25. Alright, so we go to stat plot, and then we go to zoom 9. Alright, so that is, let's see, that's not, Alright, so if I was to draw a line of best fit here, this looks like it's going this way. It's not curved, it's not parabolic, so I'm going to say this is a fairly weak negative linear association between x and y. You know, you might be saying, well, Mr. O'Neill, I don't really see a great line there. Well, the bottom line is a line could be drawn through there. If I was to say you were to draw a curve, parabola, or a line through that data set, what would be your best option? Most likely it would be a line, though it's not a great relationship. So let's see what happens when we go to stat calc and we get a correlation here. So let's see, yeah, see our correlation is negative 0.302. So this is moderate, this is negative. We drew the line the right way, and it's definitely weak. 0.3 is getting closer to 0 than it is to 1, or negative 1. So it's not a very strong relationship. Alright, let's do this one here. So we got 10 through 70, 2, 4, 8, 16, 32, 64, 128. Now I'm just going to push zoom stat and look at that. Okay, so I have let's describe this. This is a strong, positive, curved association between x and y. So in this case, I'm not going to calculate the correlation because it's not applicable. I don't calculate a correlation of a curve relationship. So in this case, I could describe it. It is strong, it is positive, but it's curved. So correlation is not going to factor into it. Let's do this last one here. Everyone's going to be 50. What is that going to look like? Well, you guessed that. It's perfectly horizontal. You are right. So this is x, this is y. Well, what's the correlation? Well, let's describe that. So that's fairly strong, isn't it? So it's linear. No direction. Actually, I wouldn't say no direction. I would say linear horizontal relationship between x and y. I wouldn't say no direction. And so then when I calculate this, I should get a correlation of 0. Let's see what we get. There. Well, didn't like that. So I said, okay, I'm not calculating that, but we know our correlation there is 0. So this last case, if women always married men who were 2 years older than themselves, what would be the correlation? Well, let's put that in the calculator. Let's figure that out. So I'm just going to clear these two out. So let's say that women start marrying, I don't know, 21, 23, 25, 27, 29 years old, 31, 33, 35. Okay, so every woman is going to marry a man that's 2 years older than herself. So in list 2, I'm just going to say, okay, take list 1 and add 2. So a 21-year-old female is going to marry a 23-year-old man, a 23-year-old female will marry a 25-year-old man, and so forth down to the 35-year-old female who will marry the 37-year-old man. And if I look at the graph of that, look at that, holy cow. So this is age female, age male, and that comes out nicely like that. And what would the correlation there be? Well, you said that it's, let's see, should be positive, right? It's actually going to be positive 1. It's a perfectly straight line. So so R equals 1. Okay. So that takes care of correlation. So correlation talks about two things. Okay, it's your R value, and the R value is applicable for a linear relationship. It is not applicable for a non-linear relationship. It's a number between -1 and +1. The closer it is to -1 and +1, the stronger it is. Okay, and the sign tells us the direction. So it tells us strength and direction. It quantifies it for us. It gives us a number. Okay. However, we do have to verify that we have a linear relationship, so we always have to look at the scatter plot. Do not look at the correlation and then just try to describe the form of it and say, oh, well, let's see, the correlation is 0.8, so it's linear. Well, not necessarily. Always look at the scatter plot. Okay? Once you verify that it's linear, then go ahead and calculate the correlation. Then you can quantify the strength and the direction. Alright, so let's look at outliers now and how they, what role they play. The R value is greatly affected by outliers. Okay, so in our graph here, there's the graph of these 5 points. We calculate the Lin regression, and we get an R value of 0.998. Strong positive, right? Strong positive linear relationship. Now, scenario 1, we're going to add the 0.35, 125. So I go into my data list, and I'm going to add 35 and 125. And I'm going to graph that. So that guy's right there. And so what this is going to look like is the first 3 points go like that, and then the 4th point, and then the 5th point, and then there's this guy. So what did it do? Well, it's no longer perfectly straight, so my correlation is still going to be positive, but it's not going to be as close to +1 as it was. It was like 0.002 away. So when I go to stat calc now, my R value went down to 0.982. So R equals 0.982, and so R decreased. Okay. Okay, so now what we got to do is we got to delete that point. And we got to delete the 0.3095, and then we're going to graph it. And now we have a graph that looks like this. And let's see what happens when we calculate our R value. I would say it's pretty straight. We started out with 0.998. So let's see what happens. It actually went up. So it's actually 0.9998. So that must mean that this point right here, this original point, ignoring that one, was slightly off the line. So R increased. Okay, it got closer to +1. Okay, so now I got to put the point 3095 back in, and I got to add the point 6100. So let's see what that looks like. Let me zoom 9 that. Okay, so that guy is right there, and guess what? My line is now not going to be perfectly straight anymore. So I had my original nice 5 points, and then there's that guy right there. So guess what R is going to do? I'm guessing R is going to not be close to 0.998 anymore. So let's calc that. 0.813. The new value is 0.813. So R decreased. Okay. So the farther the outlier is off, the more effect it has on your R value. So we got this situation here. Archaeologist is an extinct beast having Archaeopteryx. It's an extinct beast having feathers but a bird, but teeth and a long bony tail like a reptile. Only 6 fossils are known. Because these specimens differ greatly in size, some scientists think they are different species. The specimens belong to the same species in a different size. There should be a positive linear relationship. An outlier would suggest a different species. So let's look at these. So I'm going to clear list 1, clear list 2. So we got 38, 56, 59, 64, and 74. And then the 41, 63, 70, 72, and 84. And we're going to take a look at a graph of that. Looks like that one, there's a one that's probably off a little bit. It's not that much of an outlier, but this one is 59. Let's see, let's trace that. It's that 59 and 70, yeah. And this one might not be of the same species, so it looks like the 4 points, these 4 points, 38, 41, 56, 63, 64, and 72, and 74, 84, make almost a perfectly straight line. This 59, 70 is not on the same line as those other 4 points, so that might suggest, doesn't mean it does, it might suggest that this fossil is not of the same species as the other 4. Okay, interpreting correlation. So the most important thing to do is remember when you're interpreting correlation is that you're talking about the strength and direction of a linear relationship. And the last thing you must remember to do is to do that in context. Okay? So, before I go on to that, let me just say, let's say we have a graph, and our graph is, let's say it's height and weight. We use height to predict weight. And let's say that it's moderate, it goes like that, and let's say that we have an R value of 0.7. So we determined that this is fairly linear, and let's say, I don't know, we're doing this for only 10th grade males. Okay, so we would say, what does this R value mean? Well, it's the strength and direction. Well, there's a moderate, positive, linear, because correlation is about a linear relationship. So moderate, positive, linear relationship. What's the context? Between height and weight of 10th grade males. That's how that has to be written. So if you're asked to interpret this, don't just say, oh, correlation's 0.7, it's moderate and positive. Well, that's not the context of the situation. It's linear, and we're talking about height and weight of 10th grade males. Okay? So each of these contains a blunder. Let's decide what's wrong. There's a high correlation between the gender of American workers and their income. Well, what's wrong with that? Well, what's wrong with that is gender is not a quantitative variable; it's categorical. So there's a high association between those two, but not correlation. Correlation is a quantitative measure of the strength and direction of two quantitative variables. So that would be wrong. We found a high correlation, R equals 1.09, between student ratings of faculty teaching and ratings made by other faculty members. Well, what's the error there? Well, ratings are both quantitative, but you cannot have an R value over 1.0. Your R value has to be between -1 and 1, so you can't have a correlation of 1.09. In part C, the correlation between planting rate and yield of corn was R equals 0.23 bushels. Okay, well, this is a quantitative variable, that's fine. Yield of corn is a quantitative variable, that's fine. R equals 0.23, that would be fine, but you can't have units. Correlation's unitless, so it's simply R equals 0.23. Okay? Alright, correlation tables show up. All these are the correlations between, a correlation between anything in itself is always 1. Okay, so if I was to do the, this is showing UConn GPA versus their high school GPA versus their SAT scores. So if I was to plot anybody's SAT score versus their own SAT score, you would get a perfectly straight line. Okay, so that's why these are all 1. This is UConn GPA, high school GPA, and SAT versus SAT. And then these are correlations between different variables. High school GPA and UConn GPA has a correlation of 0.6. SAT scores and UConn GPA has a correlation of 0.85. SAT scores and high school GPA has a correlation of 0.9. So what is the correlation between SAT scores and high school GPA? Well, SAT scores and high school GPA is right here. It's R equals 0.9. What generally has a stronger connection to UConn GPA? High school GPA or high school math scores? Well, high school GPA has a correlation of 0.6. SAT scores has a correlation of 0.85. So it would be SAT scores have a stronger connection to UConn GPA than high school GPA does. Alright, so the last thing that we're going to look at is a very important concept, and it's association versus causation. So we have a graph, number of Oreos eaten and weight gained. So in the graph shown, the number of Oreos eaten versus the weight gained, R equals 1. Perfectly straight line. However, this does not imply causation. We cannot say that number of Oreos eaten caused weight gain. What we can say is there is a very strong association between number of Oreos eaten and weight gained. What's the difference between these two? Well, the difference here is we are here saying there's only one variable that caused weight gain. Well, there might be other variables that cause weight gain. Okay, it could be that people who eat a lot of Oreos don't exercise a lot, whereas people who don't eat a lot of Oreos tend to have a more active lifestyle. So we can't necessarily attribute it all to Oreos. Okay, so we can say, hey, there's a pretty strong association here, but we can't just say that Oreos are the only cause of weight gain. So that's the difference in the two statements. So this does not imply causation, meaning that eating more Oreos will cause someone to gain weight. There could be other variables, lurking variables we can identify, such as people also eat cake or ice cream? Well, maybe people who eat a lot of Oreos eat a lot of junk food. All right, their diet may not be good, so it could cause them to gain weight. Confounding variables such we cannot pin down, such as metabolism, or activity of lifestyle. Okay, like I talked about, could be that people who are over here are more active. We don't know. Alright, so we can't just say, well, it's just Oreos that cause weight gain. We would have to look more closely at what their lifestyle habits are.